We've looked at a few different approximations for the definite integral, and in fact, developing the definition of the definite integral, we looked at rectangles using right endpoints, left endpoints. Well, today he introduced the trapezoid rule, where instead of using rectangles, we use trapezoids, which geometrically looks like a much better fit than what the rectangles were. Just to kind of give you a curve here. And if we do this, maybe it's half a unit wide, well, our rectangles would look like that, where the trapezoid, well, gets really, really close. Well, today we're going to go one step beyond the trapezoid and introduce a rule based on an area formula you've probably never seen before, but it exists, and that's the area under a parabola. So instead of, again, using rectangles or trapezoids, we're going to partition the interval in a way we can use parabolas rather than the trapezoids. And that area formula under a parabola, 1/3 times x sub 3 minus x sub 1 over 2, and then y sub 1 plus 4 y sub 2 plus y sub 3. Now the y values, y1, y2, y3, those are the function values that goes along with x1, x2, and x3. And we have not defined here what the x's represent. Okay, the x1 and x3 are the endpoints of the interval we're looking at, and x sub 2, well, that's going to be the average of those endpoints, or basically halfway between x sub 1 and x sub 3. And the only place x sub 2 shows up would be the function value for that x value, this y sub 2. Okay. So anyway, this is the area formula under a parabola. Any of you seen that before? No, I had never done that either until I started teaching this particular rule. But notice that we're dealing with 3 different y values, and the first one and the last one are both just one of those, but the middle one is 4 times that y value. Okay. Yeah. Question.
Because of 4 rectangles? Or?
Well, this is the parabola based on area under a parabola, so it's just the way it turns out to be. Now, I'm not going to prove this, show this to you, but it does work. In fact, I will show you at least. Let's look at the area under, let's see, x squared plus 2x from x equals 1 to x equals 4. And just to give you a little idea of what that looks like, 1, 2, 3, 4. At 1, we'd be at what? Y value of 3. And at 4, 16 and 8, 24. So again, I have kind of really distorted my graph because can't hardly fit it on there. Now that's a parabola, not a straight line, not a squiggly line like I drew. Well, the area formula will be able to calculate this exactly. Now we will need, this will be the x sub 1 and this will be x sub 3. X sub 2 will be what? Well, yeah, 4 plus 1 would be 5 and then take half, so 5 halves or 2.5. So plugging it into this, 1/3 times 4 minus 1 over 2, and then, well, y sub 1, we already calculated that, would be 3, plus 4 times y sub 2. Now y sub 2 gets a little ugly. Plug 5 halves into our function here. 5 halves squared would be 25/4 plus 2 times 5 halves, well, plus 5. So 25/4 plus, well, we'll just put it in this way. Whatever that would be.
5/4.
Okay. And then plus y sub 3, what did we say that was, 24? Okay, and calculate all that. The area, exact area in here will be what? So from our area formula, again, this very popular area under a parabola, or maybe not so much. Area is 36. What's another way we could show that this is true? Okay, the integral. What's the area of this region? Well, we can set it up as an integral, which no wonder this area formula is not used, because the integral is much easier to work with. We integrate from 1 to 4, x squared plus 2x dx, antiderivative. Evaluate from 1 to 4. And, well, calculate that. Guess what we get? Yeah, we get 36. So probably after they figured out the integral is so much easier to calculate with the fundamental theorem, this area under a parabola formula kind of got tossed aside. But we're still going to be using this idea, this basic formula, to develop an approximation, and thinking about how we would take the area under some curve over a fairly large interval. We can partition it somehow, and maybe we'll partition it into 12 parts or 6 parts or 20 parts. Well, our first 3 partitions, well, actually, y sub 1 would come from our, what we've been calling x sub 0, okay, the a where we start. So a, and then x sub 1 and x sub 2, those would give us our first kind of parts of this formula. Then x sub 3, x sub 4, and x sub 5 would give us our next approximation from this formula. And this value here will actually show up twice as we add the approximation over and over again. This will be the last value of our first partition, and this will be the first value of the second partition. And so each of these values here kind of in the middle of our partition shows up twice when we use it to calculate the area. Okay. So what we call Simpson's rule follows from this right here. So Simpson's rule is, well, the form for the area under the parabola formula, we had the 1/3, then we had the x sub 3 minus x sub 1, which in terms of our integral will be the b minus a, and then over 2, well, that was where we just split that one huge interval in half. So it's going to be b minus a over n. And where have we seen that before? That's delta x. So that is where that x sub 3 minus x sub 1 over 2 comes from when we separate that interval into two parts. Okay. And then the function value, well, the y sub 1, as we talked in our area under a parabola, that's going to be the function value at a, or x sub 0. And then 4 times our next x value in our partition. And then plus, well, the y sub 3 in our parabola formula, that would be f of x sub 2. Okay, that would be the last part of our first approximation, but then we add the parabola formula for the next part, and the first portion of that will be f of x sub 2 as well. So we end up with 2 of these f of x sub 2. Then, with our parabola formula, 4 of the middle one, and then back to 2, and really it just alternates. And then finally the last, well, we'll need to show the last 2 terms of this would be at our middle one, for the parabola, and that's going to be x sub n minus 1, and then plus our very last one, well, it's only going to show up once. Okay, we're not going to have the 2 times that, because the very last parabola approximation we only use f of b, or the f of x sub n, once. Okay, it's not the last one on one and then the first one on the other. And we stop at that point. So essentially, the coefficients of our function values fill in the pattern 1, 4, 2, 4, 2, 4, 2, 4, and then 1, and that's it. So, which the trapezoid rule, it's actually fairly similar to this, but we don't have the 3 parts to worry about there. It's 1/2 times the b minus a over n, and then times f of x sub 0 plus 2 f of x sub 1 plus 2 f of x sub 2, and so on, plus 2 f of x sub n minus 1, and then finally, again, just the 1 at our endpoint. So the approximations, we can now get a lot more accuracy using these approximate formulas rather than using rectangles and right endpoints and left endpoints and so forth. Let's go ahead and find the exact value on this, and then I'll show you the approximations and how close some of the approximations are anyway, how far off some of the others are. Well, what do we need to do first?
You can rewrite it.
Recognize that's x to the -2, and so as we do our integration and from 2 to 3, so let's see, we'd have -2 1 over x from 2 to 3. 1/3 minus 1/2, or since we have the 2 out here, we could say -2/3. Let's go ahead and multiply that through. -2/3, plus 1, and well, -2/3 plus 1 is exactly 1/3. Okay, so there's our exact value. Now let's see how we do this with Simpson's rule. And let's go with n equal 4. Okay. Now, for Simpson's rule to work, we have to have an even number of partitions, as you might think, where the x sub 2 in our formula was the midpoint of our interval. So that's one restriction we have to have. We can't just let n equal anything. But if n is 4, well, Simpson's rule is 1/3 times the delta x, b minus a over n, and then we'd have f of x sub 0, which is our 2, plus 4 times f of x sub 1, which would be what? 2 1/4. Okay. Delta x is 1/4. Okay. And we're starting here at 2, so x sub 1 is 2 1/4. Then we'd have 2 times x sub 2, which would be what? 2 1/2, plus, well, back to 4 times 2 3/4, and then finally we're down to our last one, which is 1 times f of 3. And of course, with calculators, it's going to be a lot easier. Use decimals rather than the fractions. Of course, some calculators take the fractions just as easy. But what we end up with doing all these calculations, Simpson's rule, we get 0.333336003129 out to how many ever decimal places that is. Like I said earlier, I calculated these so we wouldn't be taking time to plug this into your calculator. So that's our Simpson's rule. The trapezoid rule gets pretty decent, but it's not nearly as close as Simpson's rule. We get a 3, 3 but then it jumps up to 5, 1, 5, 8, 9, 1, 2, 3, 5, 6. So at least almost to 2 decimal places, where trapezoid goes almost to 4 decimal places. Yeah. Now we do the approximation here. We were able to find the exact value, but a lot of things in the real world, we're not going to be able to find the exact value. And there's some good illustrations on the homework or the worksheet that shows that. And so here's our right endpoints and left endpoints. Definitely not near the accuracy of even the trapezoid, but Simpson's rule is by far the most accurate. And in applications and in fact, a lot of real-world situations, we won't be able to calculate exact values. On the job, if you have to do some kind of application with calculating a definite integral, you'll probably just plug it into a computer program and it's going to calculate an approximation. But we want the approximation to be, or the computer program to be as efficient as possible. We don't want to wait an hour for the results, so we want to start out with as most accurate as possible. So definitely would not be using these, not even that. Now, your graphing calculators, some of those have approximations programmed in it. And I'm not sure if they use Simpson's rule or if they use some other program. Texas Instruments and these other calculator companies try to keep those kind of under wraps. So, but they haven't told me about them anyway. But you can kind of get an idea how they do approximate definite integrals. So Simpson's rule, trapezoid rule, we'll be looking at a few problems with that. And some of the problems you'll be able to compare to the exact value, just to see how close we get.